Welcome to Sequences and Series for Pre-Calc11, and we're taking a look at Geometric Series, Section 1.4. In previous screencasts, we've seen geometric sequences, we've seen arithmetic sequences and series. So the extension to this is, let's take a look at geometric series. So it's much the same as a geometric sequence, except we're going to separate terms by adding them together. So let's start with one. Let's say we start with 2 and we're multiplying by 3 to give us 6, 18, etc., etc., etc. We see that the first term here is 2 and the common ratio is 3. This is a growth series because terms are getting bigger and bigger. What else? Let's try a different one. 16 as a first term. Let's say we're dividing by 2 or multiplying by a half, and let's even make it an alternating series. So let's multiply by a negative half. So 16 minus 8, then the next one would be positive 4, the next one would be negative 2, etc., etc. Term 1 is 16, common ratio is negative a half, and this is a decay series. So we saw growth and decay series from the last screencast on geometric sequences. So pretty straightforward. Again, specific terms are found by using that standard T sub n formula. So specific terms, T sub n is T1 times R to the n minus 1. That hasn't changed for specific terms. But let's talk about, if we're talking about a series, it's interesting to talk about what do these things add up to. So let's, for instance, start with a few terms here. If we have, for instance, the first term, second term, and third term, let's just build a little table here. Let's say the first term is T1, second term is T1 times R, third term is T1 times R squared. Let's even go to the fourth term, T1R to the 3, and that's going to continue. And what we plan on doing is we plan on adding these things up. So if we took a look at our first example, let's say 2 plus 6 plus 18, term 1 is 2, term 2 is 6, term 3 is 18, term 4 again times 3 would be 54. And what we can do is just add these up. So certainly S1 would be 2, S2 would be the sum of the first two terms, 2 and 6 is 8, S3 would be 2 plus 6 plus 18, that would be 26, and again we could just keep adding terms. But what about in general? S1 is just T1, S2 is term 1 plus term 2, S2 is term 1 plus term 2 plus term 3. So we see this pattern continue. Term 1 plus term 1R plus term 1R squared plus term 1R cubed. And what I've done here is I've generalized that. For instance, if we had n terms, at some point this finite series with n terms is going to have a last term of T1 R to the n minus 1. So that's that term right there. That should make sense because that is just the general term for a geometric series. So let's see what we can do here. To develop the actual formula, we need to actually multiply the above formula by R. So let's write down what R times Sn is. The term 1 times R is going to be term 1R. I'm just actually moving it over to the right slightly for a reason. Term 1 times R, here term 2, will give us T1R squared, T1R cubed, T1R to the 4, and then I hit my plus sign and a whole bunch of dots. Here's the tricky one. If I multiply T1Rn to the minus 2 by an R, I'll only have minus 1R. And the last term should be T1R to the n. So coming up with an equation, we have Sn, and we have RSN. And the little trick here is we're going to subtract these two formulas. Column subtract. So on the left hand side, SN minus RSN, there's our equal sign. Notice that the T1R up top is going to cancel with this T1R on the bottom. That's why I've shifted it over a little bit. T1R squared, let's even change a little colors here just so we can see all the things that cancel. Now, T1R to the 4, I don't have up top, but because I've generalized, I know it's there somewhere. I just didn't bother writing it down. So we have T1RN minus 1 canceling off with T1RN minus 1. And we have T1RN minus 2. I don't see that on the bottom, but I know that has to appear in there somewhere. So what do we end up with? We end up with an extra T1 up top, subtracting a T1R to the n from the bottom. Let's go through this. We're actually going to go two different directions with this. The first thing we could do is factor out what we can from both sides of the equation. So on the left hand side I could factor out S sub n. On the right hand side I could factor out T1. Solving for Sn, and to do that we're going to divide by 1 minus r. There we go. There's a great formula for the sum of the first n terms of a series. Let's maybe write that down. Sn is T1 1 minus r to the n over 1 minus r. A little bit more complicated than the other ones, but still works. We can further develop this formula by factoring out a negative sign out of both the top and bottom brackets. And what we're going to end up with is a negative 1 plus r to the n over, factored out a negative 1, sorry, not a t there, an r minus 1. The negatives cancel and we're left with T1, and let me just reorder a bit, r to the n minus 1 over r minus 1. So again, that's another version of the exact same formula, and this one you may not really want to bother remembering. It's only maybe useful sometimes when the common ratio is a certain type of number, and we'll talk about that later. Where I want to deviate maybe from this formula here a bit is if we develop almost a completely different formula. So we have Sn minus RSn equals T1 minus T1 r to the n. Still great. On the left hand side we're still going to factor out s to the n, s sub n I should say. What I'm going to do on the right hand side here is something a little bit different. What I want to do is just out of that second term I'm going to factor out an r, leaving me with T1 r to the n minus 1. Sn 1 minus r stays the same, T1 is the same, r is the same. Notice now though that T1 times r to the n minus 1, what does that look like? It looks like the general equation for the last term in the series, T sub n. So solving this for S sub n, we get T1 minus r Tn over 1 minus r, where that Tn is the last term. So this is only really going to work for a nice finite series. So if we're given a finite series and we're given the last term, we can certainly use that formula. It's not imperative. We can get around that a little bit, but we can certainly use that formula to figure out the sum. Thus ends the notes for geometric series, and what follows will be some examples.